Hello everyone, I Abhishek Misal from CSVTU Bhilai welcome you to on this massive online course. The name of this course is Fundamental of Communication System and its Application. Today we will continue on a fascinating journey into the world of digital communication. In previous lecture, you study about the digital signal representation where the analog signal is converted to the digital signal. In the previous lecture, we studied the different type of signals representation. In this lecture, we study the one step of converting the analog signals into the sample. Now let's discuss the sampling. Sampling is initial step in converting an analog signal to a digital one. It involves measuring the amplitude of analog signal at regular interval. These intervals are determined by the sampling rate, which must be carefully chosen to ensure accurate signal representation. According to the Nyquist-Shannon sampling theorem, the sampling rate must be at least twice the highest frequency present in analog signal. This rate known as the Nyquist rate, preventing aliasing, a phenomena where higher frequency component of the signal become indistinguishable from lower frequency component, leading to distortion. Now we discuss the sampling. In the communication system, the concept of modulation is crucial for transmitting signal at higher frequency rather than at baseband frequency. Modulation techniques such as amplitude modulation, frequency modulation and phase modulation play a significant role in this process. The primary goal of sampling is to capture enough information from the continuous signal to accurately reconstruct it later. Nyquist-Shannon sampling theorem. The Nyquist-Shannon sampling theorem is the cornerstone of digital signal processing. It states that a continuous signal can be completely represented by its sample and perfectly reconstructed if it is sampled at a rate greater than twice of its highest frequency component. The rate is known as Nyquist rate. Mathematically, if xt is a band limited signal with a maximum frequency fm, the sampling frequency fs must satisfy the condition, that is fs is greater than 2 fm. Here we discuss detail the Nyquist-Shannon sampling theorem. The Nyquist-Shannon sampling theorem is a fundamental principle in the field of signal processing and communication. It provides the theoretically foundation for converting a continuous time signal into a discrete time signal and back without losing any information. This theorem has profound implication in various domains, including audio processing, telecommunication, medical image processing, and digital media, historical and background. The theorem is named after Harry Nyquist and Claude Shannon. Nyquist in 1928 laid the groundwork by studying the maximum data rate of a transmission channel, while Shannon in 1948 expanded on this idea and formalized the sampling theorem as part of this work of information theory. The Nyquist-Shannon sampling theorem is a very important in digital signal processing and communication theory. It provides the fundamental criteria for accurately converting a continuous time signal into discrete sample and subsequently reconstructing the original signal from those samples without any loss of information. Understanding this theorem is essential for ensuring the fidelity and integrity of signals in digital system of digital system. The statement of this theorem is the Nyquist-Shannon sampling theorem states that a continuous time signal xt can be perfectly reconstructed from its sample xn if the sampling frequency fs is at least twice the highest frequency component fmax for the signal. Mathematically, this can be expressed as fs is greater than or equal to 2fmx, where the fmx is the maximum frequency and fs is the sampling frequency. The minimum required sampling frequency fs is known as the Nyquist rate and it is represented by fn is equal to fs by 2 is the Nyquist frequency. The mathematical foundation of this theorem is consider a band limited signal. This signal can be represented as xf is equal to 0 for mode of f is greater than f max when sampled at interval of ts is equal to 1 upon fs. The sample signal xst is given by xst is equal to xt is equal to into summation of the limit is n is equal to minus infinity to infinity del in the bracket t minus n ts the bracket close. The Fourier transform of the sample signal xsf is xsf is equal to 1 upon t summation of the lower limit is k is equal to minus infinite and the maximum limit is infinity into x in the bracket f minus k upon ts bracket close. If fs is greater than 2f maximum, the shifted replicas of xf in xs in the bracket f do not overlap, allowing for perfect reconstruction using an ideal low pass filter. Reconstruction process. To reconstruct the original signal xt from sample signal xst, an ideal low pass filter with a cutoff frequency fc is equal to f max is used. The filter eliminates the high frequency component introduced by the sampling process and retain only the original frequency component. The reconstructed signal t is the t in the bracket is equal to summation of the lower limit is n is equal to minus infinity to infinity and x in the bracket n into sin c in the bracket once again the bracket t minus n ts bracket close upon ts, where the sin c in the bracket t is sin in the bracket pi t upon pi t. Practical consideration. Here the major problem is aliasing. If the sampling frequency fs is less than twice highest frequency component of the signal, aliasing occur. Aliasing is the overlap of spectral replica resulting in distortion and loss of information. To avoid aliasing, the signal must be band limited or pre-filtered using an anti-aliasing filter before sampling. Finite bandwidth signal. In practice, signals are not perfectly band limited to approximate ideal condition. Signals are filtered to limit their bandwidth, ensuring minimal aliasing and distortion. No ideal filter. Real world filters cannot achieve the perfect rectangular frequency response of an ideal low pass filter, However, practical filters such as Butterworth or Chebyshev filter can approximately the ideal response and provide satisfactory reconstruction quality. Here we discuss the application and implication. The Nyquist-Shannon sampling theorem has profound implication and various fields including telecommunication, audio processing, medical image processing and data compression. It guides the design of an analog to digital converters and digital to analog converter, ensuring accurate signal representation and transmission. Adherence to the theorem criteria enables the efficient and reliable conversion between analog and digital domain, facilitating model digital communication and processing system. Here we discuss the type of sampling. Sampling method can be categorized based on how the sample are taken from continuous signal. The most common type of sampling are ideal sampling, or it is called impulse sampling, natural sampling. The third is flat top sampling. Now first discuss ideal sampling in the bracket or using we are called impulse sampling. Ideal sampling, also known as impulse sampling, is a theoretical concept where continuous time signal is multiplied by a train of a direct delta function. This operation results in a sequence of impulse, each corresponding to the sample value of the original signal at discrete time interval. While this method provides a perfect theoretical framework for understanding the sampling process, it is important to recognize that it cannot be implemented directly in practical system due to the nature of direct delta function. The mathematical representation is mathematical ideal sampling is expressed by x s t is equal to x t multiplied by summation. The lower limit is n is equal to minus infinity to infinity del in the bracket t minus n t s bracket close. Here x s t represent the sample signal, x t is original continuous time signal, t s is the sampling interval and del t is the direct delta function. The sampling frequency fs is given by fs is equal to 1 upon ts. In this equation, the original signal xt is multiplied by a train of direct delta function spaced ts second apart. The result is a series of impulse, each with amplitude equal to the value of the original signal at the corresponding sampling instant. The advantage of ideal sampling: theoretically perfect representation. Ideal sampling provide a perfect theoretical representation of sample signal. Each impulse in the sample signal exactly capture the value of original signal at the sampling instant. That makes the mathematical analysis and understanding of the sampling process straightforward and precise. Simple mathematical analysis: the use of direct data function simplify the mathematical analysis of sample signal. The Fourier transform of train of direct delta function is also a train of direct delta function with make the frequency domain analysis of sample signal easier. This property is essential for deriving important result in signal processing such as Nyquist-Shannon sampling theorem. Disadvantage of ideal sampling: impracticality of implementation. The primary disadvantage of ideal sampling is that it cannot be implemented in practice. The Dirac delta function is an idealized mathematical construct with infinite amplitude and infinitesimal width which cannot be realized in physical system. As a result, ideal sampling serve as a theoretical model rather than a practical technique. Need for approximation in practical system. Due to the impracticality of using the Dirac delta function, practical sampling system must be approximation such as pulse amplitude modulation or other type of sampling technique. These approximation introduce certain limitation and imperfections such as quantization, noise and aliasing, which need to be managed in real world application. Natural sampling. Natural sampling is a practical approach of sampling continuous time signal used to approximation the ideal sampling process. Unlike ideal sampling, use Dirac delta function to the sampling. Natural sampling employs a series of rectangular pulses that follow the shape of original signal during each sampling interval. The method is more feasible for implementation in real system world, provide before representation of the signal compared to simpler method like flat top sampling. Mathematical representation. In natural sampling, the continuous time signal xt is multiplied by a train of rectangular pulse resulting in a sampled signal xt. Mathematically, this can be expressed is x in the bracket t is equal to xt in the multiply by p in the bracket t, where pt is a periodic pulse train given by pt is equal to summation of n is equal to minus infinity to infinity rectangular in the bracket t minus nts upon tau. Here rectangular is the RECT in the bracket dot is the rectangular function, ts is the sampling interval and tau. Tau is the width of each rectangular pulse. The rectangular function RECT upon t upon tau is defined as a 1 if t mod of t is less than equal to tau by 2, otherwise 0. Below is a diagram illustrating the concept of natural sampling. Advantage of natural sampling: better approximation of the original signal. Natural sampling provides a more accurate representation of the original signal compared to flat top sampling. By maintaining the shape of signal with each sampling interval, natural sampling reduce distortion and better preserve the signal characteristic. Feasible for implementation. Unlike ideal sampling, which require Dirac delta function, natural sampling use rectangular pulse that can be generated and processed in the practical system. This makes natural sampling a viable option for real application. The sampler reconstruction. The sampled signal is natural information about the original signal, making the reconstruction process easier and more accurate. The interpolation of the sampled signal to the recover the original continuous time signal is more straightforward. The disadvantage of natural sampling. The first disadvantage of natural sampling is finite pulse width. The finite width of rectangular pulse in natural sampling introduce a slight deviation from the ideal sampling process. This can result in some loss of high frequency component of the original signal. Complexity in pulse generation. Generating rectangular pulse that accurately follow the shape of original signal with each sampling interval can be complex and may require sophisticated critically aliasing. Like all sampling method, natural sampling is susceptible to aliasing if the sampling frequency is now high enough. The Nyquist-Shannon sampling theorem must be followed to avoid aliasing and ensure accurate signal representation. The next sampling technique is flat top sampling. Flat top sampling is a practical method of sampling a continuous time signal where each sample is represented by a rectangular pulse of constant amplitude. This method is commonly used in digital communication system due to its simplicity and ease of implementation. However, it introduces some distortions and require careful handling to ensure accurate signal and reconstruction. Mathematical representation. In flat top sampling, the continuous time signal xt is sampled and held at a constant value for specified duration tau with each sampling period Ts. Mathematically, flat top sampling can be expressed as x s t in the bracket t is equal to summation of the lower limit is n is equal to minus infinity to infinity into x n ts rectangular t minus n ts upon tau. Here x s t is the flat top sampled, ts is the sampling interval, x n ts is the sample value of n minus th sampling instant a rectangular in the bracket t minus n ts upon tau is the rectangular pulse function defined as 1 if the in the bracket tau is less than equal to t by 2, otherwise 0. The rectangular pulse has a duration tau and a constant amplitude equal to the sample value x and ts. Advantage of flat top sampling. Simple implementation. Flat top sampling is a straightforward to implementation using sample and hold circuit which are commonly available in digital analog to digital converter. This simplicity to make digital communication process. Ease of processing. The constant amplitude of rectangular pulse simplify the process and analysis of the sampled signal. Digital system can easily handle the discrete uniform amplitude level. The disadvantage of flat top sampling. Amplitude distortion. The primary drawback of flat top sampling is amplitude distortion, also known as aperture effect during the flat top sampling process. The signal is held constant over the duration of pulse, which can lead to inaccuracy, especially for high frequency component. This cause distortion the construction signal. Increased aliasing. Flat top sampling can introduce additional aliasing compared to ideal or natural sampling. The flat top pause effectively modulated to the signal, which can lead to spectrum spreading and increase aliasing if its sample frequency is not sufficient high. Reconstruction challenges. Accurate reconstruction of original continuous time signal from flat top sample data can be more challenging technique like disadvantage. To address the challenges posed by flat top sampling, several technique can be employed. Higher sampling rate. Increasing the sampling rate can help mitigate aliasing and reduce amplitude distortion according to the Nyquist-Shannon sampling theorem. The sampling rate should be least twice the highest frequency component of signal. Aperture correction. Aperture correction technique can be applied to compare for distortion introduced by the flat top pulse. These flat top pulse, this involve adjusting sample value based on the known distortion of sampling. Now, filtering. Pre-sampling and post-sampling filtering can use to reduce high frequency component and smooth the signal, therefore reducing distortion and aliasing. Now, we discuss the quantization. The quantization concept and type. Quantization is a crucial process in digital signal processing, where a continuous range of volume, large set of discrete value is mapped to a finite set of discrete value. This process is essential for converting analog signal into digital signal, enabling them to be processed, stored and transmitted using digital signal. The concept of quantization is the first definition. Quantization is the process of approximation a continuous range of value or a large discrete cell with a smaller set of discrete values. In this context, analog to digital conversion ADC is refer to a maximum amplitude of an analog signal to discrete level. The mathematical representation is shown here. Now, we discuss the quantization error. Quantization introduce an error known as quantization error, defined as the difference between the input signal and the quantized signal, which is represented by Et is equal to x t minus q in the bracket x t. The quantization error depend on the number of quantization level and the method used for quantization. The different modulation technique, that is the first modulation is pulse modulation of signal. In many cases, the communication link bandwidth is much greater than the signal bandwidth. The signal can be transmitted using short pulse with the low duty cycle. Pulse modulation techniques include pulse amplitude modulation, that is called PAM. The width is fixed but the amplitude vary. The next technique is pulse width modulation. The position is fixed but the width is vary. Now, we discuss the next technique is pulse position modulation, that is PPM. The width is fixed but the position vary. These method can be used time division multiplexing to carry multiple signal over that. Now we first discuss the pulse amplitude modulation. The concept of PAM involve varying the amplitude of the pulse in the proportion of amplitude of the message signal. This technique is simplest form of pulse modulation. The mathematical representation shown here and the block diagram is also shown. You can see and understand. The advantage is it is simple implementation, efficient for transmitting analog signal in digital form. Disadvantage, susceptible to noise and interference, require high bandwidth compared to analog modulation. Now the next technique is pulse width modulation. It involves varying width of the pulse in accordance with the message signal while keeping the amplitude constant. This modulation technique is widely used in power delivery and control. Advantage, more resistance to noise compared to PAM, efficient power delivery and more complex to greater the demodulations. Now we discuss the another technique, that is pulse position modulation. The pulse position modulation involves varying the position of pulse relative to a reference position according to the message signal. The amplitude and width of pulse are kept constant. With the help of this, you can easily understand the pulse amplitude modulation, pulse position modulation and pulse modulation. I hope you understand the sampling, quantization and different modulation technique. I thank you to all for listening, patience listening on this topic. Thank you.